Hi, this is Qiao Chu at Lehigh University. Today we're going to talk about the problems in homework 3. Let's take a look at the first problem. Here is a pipeline system was being used to drain the water from point A to B. The total discharge is 50 cubic feet per second. The length and the diameter for pipeline 1 and 2 are given. The water temperature is equals to 39 Fahrenheit. We can find the value of specific weight of water and the kinematic viscosity on the textbook. The roughness of the pipe is equals to 0.0012 feet, and the coefficient for the bend loss is equals to 0.2. In this problem, we want to use Hardy-Krauss principles and the method of equivalent pipes to calculate the flow rate in pipeline 1 and 2, and then to determine the head loss between these 2 points. Let's take a look at the first method, which is Hardy-Krauss principles. Because the roughness and diameter are given, we can calculate the relative roughness in each pipe. For the pipe 1, the relative roughness is equals to 0.0008, and for pipeline 2, the relative roughness equals to 0.0006. Because we do not know the velocity in pipeline 1 and 2, we assume the flow in these 2 pipes are all complete turbulence. Then, based on the Moody diagram, we can read the friction factor in pipeline 1. It equals to 0.019, and the friction factor in pipeline 2, it equals to 0.0175. And then let's write down the head loss from point A to B by using the pipeline 1. It equals to the friction loss in pipeline 1 plus the minor losses. In this problem, the minor losses are caused by the bends. The friction loss is given by the Darcy-Weisbach equation. It equals to the friction factor times the length over diameter times velocity over 2g. Plus the bend loss, it equals to, because there are 2 bends in pipeline 1, so it should be 2 times the coefficient times the velocity square over 2g. If we write down the head head loss equation by using the pipeline 2. Similarly, it equals to the friction loss in pipeline 2 plus the bend loss. It equals to friction factor times L2 over D2 times velocity square over 2g plus 2 times coefficient times the velocity head. If we combine these two equations, then we can get F1 times L1 over D1 times velocity square over 2g plus 2 times coefficient times velocity head equals to F2 times L2 over D2 times velocity head plus 2 times coefficient times the velocity head. Because we already know the value of friction factor, the length, diameter, and the coefficient, then we can bring this value back to this equation. Then we can get 0.019 times 400 over 0.5 plus 2 times coefficient is 0.2 times V1 square over 2g equals to 0.0175 times 300 over 2 plus 2 times 0.2 times V2 square over 2g. Then we can get a relationship between the V1 and V2. We can get 656 V1 square. It equals to 363 V2 square. We can represent V1 and V2 by using their corresponding flow rate. The V1, it equals to Q1 over A1. It equals to 4Q1 over pi times D1 square. It equals to 0.566 times Q1. B2, it equals to Q2 over A2 equals to 0.318 times Q2. Then, if we bring these two values back into this equation, then we can solve the relationship between the Q1 and Q2. Q1, it equals to 0.418 times Q2. Because we know the Q1, the flow rate in pipeline 1 plus the flow rate in pipeline 2 equals to the total flow rate. It equals to 50 cubic feet per second. Then Q1 plus Q2 equals to 50 cubic feet per second. After resolving these two equations, we can get the flow rate. In pipeline 1, it equals to 14.7 cubic feet per second. And Q2, it equals to 35.3 cubic feet per second. Because in the previous steps, we assume that there is complete turbulence in pipeline 1 and 2, and then get a friction factor in these two pipelines. The next step is to validate our assumption. So we need to check in the value of friction factors. We already know the value of flow rate in each pipe, and based on this equation, we can calculate the velocity. So V1, it equals to 0.566 times Q1. It equals to 8.32 feet per second. And V2, it equals to 0.318 times Q2. It equals to 11.2 feet per second. And then we can calculate the Reynolds number. The Reynolds number for pipeline 1 equals to V1 times diameter over kinematic viscosity. It equals to 7.38 times 10 to the power of 5. And the relative roughness, we just calculate, it equals to 0.0008. And then, based on the Moody diagram, we can read the value of friction factor. It close to our assumption. And if we calculate the Reynolds number in pipeline 2, it equals to 1.33 times 10 to the power of 6. And the Reynolds number is equals to 0.0006. And after we read the value from Moody diagram, we find the friction factor in pipeline 2, it equals to 0.0175. It equals to our assumption. Then we can use the parameter in pipe 1 to calculate the head loss. And we have equation here. It equals to friction factor times length over diameter plus 2 times the coefficient times the velocity had. If we bring the value back into this equation, we can get equals to 0.019 times 400 over 1.5 plus 2 times 0.2 times the velocity is over there is 8.32 square over 2 times 32.2. Then we can get a value of head loss from A to B. It equals to 5.88 feet. So the result by using the Hardy-Krauss principle is this one, and the flow rate in pipeline 1 and 2 are shown here. Let's quickly go through the steps we did to solve this problem by using Hardy-Krauss principles. Based on the given data, we can calculate the relative roughness, and we assume there is a complete turbulence in these two pipes. Then we can read the friction factor in Moody diagram. And the next step is to write down the head loss equation in pipeline 1 and 2. Then based on these two equations, we can build a relationship between the velocity in pipeline 1 and 2. And because we can represent the velocity by using the flow rate over the corresponding cross-sectional area, after we join these three equations, we can get a relationship between the velocity, flow rate 1 and flow rate 2. And according to the problem, the total discharge it equals to 50 cubic feet per second. The Q1 plus Q2 equals to 50 cubic feet per second. After we join these two equations, we can solve the value of flow rate in pipeline 1 and 2. Because the friction factor we use to calculate this value is based on our assumption, so the next step is to checking the value of the friction factor. Because we already calculate the value of flow rate in pipeline 1 and 2, based on the equation here, we can get a value of velocity in these two pipelines. And then we can calculate the Reynolds number. And based on the relative roughness, we can read a new friction factor in Moody diagram. And after we checking the new friction factor in these two pipelines, we find that we made a good assumption. Then we can bring the friction factor and the velocity back into this equation to calculate the value of the head loss. And then we can get a final value of head loss from point A to B. It equals to 5.88 feet. After solving this problem by applying Hardy-Krauss principles, let's try the method of equivalent pipes. Finally, we have three unknowns. Here are the equivalent diameter and equivalent length of the pipe and equivalent friction factor. We can assign the value to two of three unknowns and then to calculate the third one based on the equation. So in this problem, we want to assign the equivalent diameter is equals to 0.5 feet. And because the roughness is given, it's over there. So we can calculate relative roughness for the equivalent pipe. It equals to 0.0012 over 2.5. It equals to 0.00048. And because we assume it's a complete turbulence flow, then we can get a friction factor by reading the Moody diagram. It equals to 0.017. Although the value of the equivalent friction factor is based on our assumption, two of three values of unknowns can be randomly chosen, so we do not need to validate our assumption later. And based on the equation 3.48 on page 68, we need to calculate our third unknown, which is the equivalent length of the pipe. Power of 5 over the equivalent length times the equivalent friction factor. It equals to d1 to the power of 5 over L1 times F1 plus d2 to the power of 5 over L2 times friction factor 2. If we bring the values back to this equation, we can get 2.5 to the power of 5 over equivalent length times friction factor is 0.017 equals to 1.5 to the power of 5 over L1 is 400. F1 is the friction factor value in pipeline 1 that we calculated by using the Hardy-Krauss principles. It equals to 0.019. And plus D2 is 2 feet. L2 is 300. 0.017. In this equation, we only do not know the equivalent length. Then, after solving this equation, we can get the equivalent length. It equals to 478 feet. And based on the Darcy-Weisbach equation given in table 3.4 on page 75, we can get the friction loss between A and B. It equals to 0.0252 times equivalent friction times equivalent length over equivalent diameter to the power of 5, then times equivalent flow rate square. In this equation, we know the value of equivalent friction factor. It equals to 0.017, and the equivalent length, it equals to 478 feet. The equivalent diameter is 2.5 feet. The equivalent flow rate is the total flow rate, which is 50 cubic feet per second. After we bring this value back to this equation, we can get the friction loss from point A to point B. It equals to 5.24 feet. And it should be noted that in this method, we neglect the minor losses. So the friction loss, it equals to the head loss from point A to B. Because the head loss from point A to B, it equals to the loss in pipeline 1. Based on the equation given here, so we can write down the head loss in pipeline 1, it equals to 0.0252 times F1, it equals to 0.019 times the length is 400 feet. It is over 1.5 to the power of 5 times Q1 square. Because we know the value of the head loss from point A to B, it equals to 5.24 feet. Then based on this equation, we can solve the value of flow rate in pipeline 1. It equals to 14.4 cubic feet per second. And because the Q1 plus Q2 is 50 cubic feet per second, 50 cubic feet per second. And then we can get the flow rate in pipeline 2, it equals to 35.6 cubic feet per second. So our result, by applying the equivalent pipes, is over there. Let's quickly review the steps to solve this problem by applying the equivalent pipes. By applying this method, there are 3 unknowns: the equivalent diameter, the length, and the friction factor. We can randomly assign the value to 2 of them. In this problem, we assign the equivalent diameter equals to 2.5 feet. And then to calculate the relative roughness, because we assume there is a complete turbulence in the flow, we can read the equivalent friction factor on Moody diagram. And based on the equation 3.48 on page 86, we can calculate the value of equivalent length. And based on the equation provided on page 75, we can calculate the friction loss from point A to B. It equals to 2.24 feet. Because in this method, we ignore the minor losses, so the friction loss, it equals to the head loss. Because the head loss from the A to B, it equals to the loss in pipeline 1. The next step is to bring the values of the parameter in pipeline 1 to the equation on page 75. Then we can calculate the value of flow rate in pipeline 1. And because the total discharge is given, we can get the value of flow rate in pipe 2. Let's move on to the problem 2. In this problem, we need to answer the following questions based on the example 4.a on the textbook. Let's look at the example question. We will read the given data and jump to the result. The procedure for solving this problem can be found on the textbook. Here is a water supply distribution system. The demands on the system are currently at junctions C, G, and F. Water enters the system at junction A from a water storage tank on a hill. The water surface elevation in the tank is 50 meters above the elevation of point A. All the junctions have the same elevation as point A. The roughness, initial flow rate, length, diameter, friction factor, and coefficient K are given in the table below. This question asks us to calculate the flow rate in the pipe. And we also need to determine if the pressure at junction F will be high enough to satisfy the customer here. The required pressure is 185 kilopascal. The solutions for the example are shown in the figure below. The flow rate and friction loss in each pipe can be found in the table on the right-hand side. Let's take a look at question A. We need to determine the pressure at junction F by accounting for pressure drops in pipes AB, BC, CH, and HF, because it asks us to calculate the pressure at point F by the pressure drops. We need to transfer the friction loss into the pressure drops first. We can do this by using the equation here. The pressure drop equals to the specific weight of water times its corresponding friction loss. The pressure at point F, it equals to the pressure at point A minus the pressure drops from point A to F. So the next step is to calculate the pressure at point A. Because we know the water surface elevation in the tank is 50 meters above the elevation of point A, so the pressure at point A is exerted by the water on the top of it. So the pressure at point A, it equals to the specific weight of water times the height. It equals to 489.5 kilopascal. And then based on this equation, we can calculate the pressure at point F. It equals to 167.4 kilopascal. The question B, it asks us to determine the lowest total energy point in the system and determine this point by inspection. Because the water always moves toward the point of least total energy, and we can see from the figure, all flows move toward the point F. The lowest total energy in the system is at the junction F. Question C. In example 4.A, it was determined that the pressure at F would be too low to satisfy the customer. What system changes could be made to raise the pressure at junction F? Because we know that all junctions are at the same elevation and the variations in the velocity heads are negligible. Therefore, the pressure at point F, it equals to the pressure at point A minus the pressure drops from point A to F. We can represent the friction loss use Darcy-Weisbach equation, and we can get this one. To increase the pressure at point F is to decrease the friction loss from point A to F, is to decrease the friction factor. And based on the Moody diagram, to decrease the friction factor, it means to decrease the relative roughness. To do that, we have two options. We can decrease the roughness or increase the diameters. So to raise the pressure at junction F, we can increase the diameter of the pipe from point A to F, or we can decrease the roughness by replace some existing pipes with newer or smoother pipes. Let's take a look at the problem 3. Here is a pipeline system as shown on the right-hand side. The water enters the system at junction A. The demands on this system are at junction D and E. We already know the water surface elevation at each junction. We also know the flow direction, initial flow rate, length, diameter, relative roughness of each pipe. This information is shown in the table below. We assume there is a complete turbulence for friction factors. In this question, we want to calculate, first, the flow rate in each pipe, second, the pressure at water demand junction D and E and compare it with 170 kilopascal by going through 2 solution iterations for each loop. Because we already know the relative roughness in each pipe and we assume the complete turbulence, then we can read the friction factor on Moody diagram. But in this problem, we want to apply another method, which is to calculate the friction factor by applying the equation 3.23. After we bring this value back to this equation, we can get the value of the friction factor, and we add this data into the table. Combining the friction factor with the length and the diameter, then we can calculate the coefficient K. The K is used to calculate the friction loss. We know the friction loss can be calculated by applying the Darcy-Weisbach equation. After we use the flow rate to represent the velocity, we can get the equation here. For a specific pipe, the friction loss, length, diameter, and cross-section area are all constant, so we want to put them together and use K to represent this term. Then the friction loss is equals to K times Q squared. The value of K, after the calculation, we can add them into the table. After we get the value of K, then we can start to calculate the flow rate in each pipe. We assume the clockwise is positive, then we can apply equation 4.15 to calculate delta Q. To do that, we need to calculate these 4 terms separately and then bring the value back to this equation. After we get the delta Q, based on their directions, we use original flow rate minus or plus the delta Q to get a new flow rate in each pipe. Let's do the first iteration in loop 1. In loop 1, there are 3 pipes. Pipe AB is in clockwise. Pipes AC and CB are in counterclockwise. Based on the difference in their directions, we put them into different groups. Then we can calculate KQ and KQ squared, and then to sum those values to get the value of these 4 terms. Then bring it back to this equation to get the delta Q. For pipe AB, because it's a clockwise, so we use original flow rate minus the delta Q. For other 2 pipes, because they are counterclockwise, then we plus the delta Q to get a new flow rate. I highlighted pipe CB here is because pipe CB is a sharing pipe in these 2 loops. So when we do the first iteration in loop 2, we need to use the new flow rate here as the original flow rate to do the calculation. Let's move on to the first iteration for loop 2. In loop 2, pipe CB, BD are in clockwise, and pipe CE and ED are in counterclockwise. And we can calculate the value based on the steps just introduced to fill up the value in this table. As we just mentioned, the original flow rate in pipe CB, it equals to the new flow rate in the first iteration in loop 1. it equals to 0.039. After we finish the first iteration, we need to do another iteration in loop 1 and 2. Then we can get the final flow rate in each pipe. The table on the right-hand side, it summarizes the value that, based on our calculation, it represents the flow rate and the friction loss in each pipe. Therefore, the first problem, solving the flow rate in each pipe, has been solved. Now let's take a look at the second problem, is to calculating the pressure at each water demand junction. At point D and E, and compare their pressure with 170 kilopascal. Let's use the junction D as an example. The total energy at point A, it equals to the total energy at point D plus the friction loss from point A to D. The total energy at point A, it equals to its elevation, which is equals to 355 meters. And we can find the value of the friction loss on this table. The friction loss in pipe AB, it equals to 9.97, and the friction loss in pipe BD, it equals to 15.75. Based on those information, we can calculate the total energy at point D, it equals to 329.3 meters. Because the total energy at point D equals to its elevation, velocity head, and pressure head, we can find its elevation in this table. And we assume the velocity, it equals to 0 at point D. Then we can get a value of the pressure at point D equals to 166 kilopascal, which is smaller than 170 kilopascal. Then the pressure
at point D is too low. Similarly, following the same procedure, we can get the pressure at point E, it equals to 182 kilopascal, which is larger than the 170 kilopascal, which means that the pressure at point E can satisfy the requirement.
Now let's take a look at the last problem. Here is a pipeline system. The water enters the system at point A. The pressure at point A, it equals to 40 psi. There are 3 points demands water in this system, which is at point C, point D, and point E. The problem provides us the information about initial flow rate, the length, diameter, and the coefficient for Hazen-Williams equation in the pipe. And it also provides us the elevation at each junction. The problem asks us to calculate the flow rate in each pipe and the pressure at each junction by applying the spreadsheet. To solve this problem, the first step is to calculate the K. Because this problem provides us the value of the coefficient for Hazen-Williams equation. Therefore, we need to apply this equation to calculate the friction loss. The friction loss in Hazen-Williams equation, it equals to K times Q to the power of 1.85. Then we can apply the equation provided on in the table 3.4 to calculate the coefficient K, which is related to the length, diameter, and the coefficient for Hazen-Williams equation. After we calculating the value of K, the next step is to calculate the flow rate in each pipe by doing 2 iterations in 3 loops. The format I used in this problem is a little bit different with the format I used for the problem 3. It is because in this problem, I following the format provided by the template posted on the course site. The difference is in this table, I did not separate the pipes based on their direction. So we need to pay more attention to do the calculation. Let's take a look at the first iteration in loop 1. After we get a value of K, we can calculate the friction loss in each pipeline. It equals to K times Q to the power of 1.85, and then divide Q. After we get all these values, we can bring it back to the equation 4.17b to calculate the delta Q. And based on their direction, we use an initial flow rate minus or plus the delta Q to get a new value of the flow rate. I highlighted the pipe BF, CF, and FG. It is because these 3 pipelines are the sharing pipes in different loops. It's BF, CF, and FG, which means that we need to pay more attention to set up their original flow rate. For instance, in pipe BF, we calculate their new flow rate in loop 1. And then when we do the calculation in loop 2, we need to set up its original value of the flow rate equals to the new flow rate we calculated in the first loop. These 2 values should equal to each other. After we do the 2 iterations for all 3 loops, we can get the final result of the flow rate in each pipe. This table summarizes the information that we got after doing 2 iterations. We listed the flow rate and the friction loss in each pipe. Because the problem asks us to calculate the pressure at each junction, we need to transfer the friction loss in each pipe into the pressure drops. By applying the equation, pressure drops equals to specific weight of water times the friction loss. So the next step is to calculate the pressure at each point. We already know the pressure at point A is equals to 40 psi. After doing the unit transformation and divide the specific weight of water, we can calculate the pressure head at point A. The total energy at point A is equals to its elevation plus the pressure head, because we assume the velocity is equals to 0. The total energy is equals to 417.5 feet. The total energy at point A can also be represented by any point. The total energy at random point in the pipeline system, plus the friction loss from point A to that point. And the total energy at that point equals to its elevation plus its pressure head. Based on these 2 equations, we can get the pressure head in a point. It equals to the total energy at point A minus the friction loss from point A to that point, and minus its elevation. After we bring the value into this equation, we can get the pressure head at each point. After we get the pressure head at each point, we can transfer it into the pressure. In this result, we find that the pressure at point D is lower than 30 psi, which means that the pressure at point D cannot satisfy the requirement. So the problem 4 has been solved.